Good evening, everyone, and welcome to the Amateur Radio General Class, session number 6. During our previous session, we had a look at the topics mutual inductance, we discussed transformers, we then talked about some calculations and did worked examples regarding transformer calculations. We looked at the various winding wire sizes, relationships. We also discussed impedance ratio and also did worked examples. We talked about wire wound type resistors. Then we looked at ceramic versus electrolytic capacitors and their characteristics. We also discussed toroidal ferrite core inductors, sometimes just simply called toroids. We also talked about the material that ferrite core inductors are made from, that's ferrite material. And then we ended the theoretical session by discussing the concept of self-resonance. And of course, we would have had a look at all of the questions in the question pool related to all of the theory that we would have covered. For this evening's session, we will be looking at the following topics. We'll discuss diodes and diode specifications. We'll talk about transistors, various types, and specifically we'll deal with a type of transistor or type of field effect transistor known as MOSFET. Then we will discuss vacuum tubes and specifically the triode. We will also talk about batteries, and then we will also deal with what are MMICs. Then we will discuss LEDs, and we will end the theory talking about some of the connectors that are used and typical in amateur radio work. Subsequent to that, we will cover all of the questions in the question pool that are related to the theory we would have covered this evening. So just a reminder for persons who are new to the general class course, we do have a previous course, level 1, which is the technician class course, and those are the links on your screen to the documents associated with that level 1. We are currently in level 2, which is the general class. So level 1, or the technician class, this is considered a prerequisite. And students who would have joined us very early on, hopefully you have been able to make a lot of progress through the technician class material. You would have seen why the technician class material is a prerequisite, and we would have also been going over some of the basic concepts in the general class as well, just to make a link or connection between the technician and the general class level, especially for those who may not have taken the technician with us before. But we encourage you to take this course. It's available on demand, and all of the videos and recordings for that level is available at this link here, tvids.ttreact.com. All right, in terms of where we are with our syllabus, so we are progressing quite nicely. We will complete the second topic this evening, that's circuit components, right? So that's the objective for this evening session. We may go a little bit over just so that we cover this topic fully, so that next week we can begin with practical circuits. Right, just a reminder of the practice exams. Please consider taking those practice exams so you will see how much material you're able to retain and know, and what's expected in the actual real exam. So also just a reminder of the React members channel on Zello. Those of the participants who would like to interact with us, we have nets on Saturdays and Mondays at 9 p.m. So check out the Zello app. So for this course that we are presently pursuing, the general class course, which is the level 2, these are the links to get all of the documents that are distributed, including slides. Every class we have, every session we have a slide deck, and we will update it. Any errata that we have, we'll make corrections to them and upload to this link. So in addition to the handout materials that we would have provided to all of the participants. All of the slides are in fact at that link, gdocs.ttreact.com. That's for this course that we are currently in. And also all of the recordings, the videos are available, the playlist at this link, gvids.ttreact.com. So if you have missed any sessions, for whatever reason, you can access them. If you want to look over something again that we did, maybe we ran a little too quickly during the actual live class, you can play it back at your pace or leisure to cover the material again. Or maybe Friday evenings are not convenient to you, or you have other things. Some people have to work, some people have other maybe religious commitments. These videos are here available at your convenience and leisure to have a look at. Okay, so we are using the No Nonsense General Class License Study Guide in the course, and we have other recommended texts should you choose to avail yourselves of them. Not required, but highly recommended. We have no outstanding questions or unanswered questions from the last session. All right, so we will put this slide up from time to time to remind ourselves that when we're talking about electronics, electric circuits or schematics, we do use the water analogy from time to time to help us understand electricity a little bit better, because we tend to be familiar with water. You know, we will maybe use a tap, we may use a shower, we may use valves, we may have pumps, we may have PVC or metallic water pipes at home, and we know water flows. Some of us may go to rivers and beaches, and we're familiar with the concepts of current and flow, and hence the reason we use the analogy. This evening, we'll also be using some of the analogies to describe electronic components. You know, we'll say, well, this is the water circuit equivalent of an electronic component. So electronic component of a resistor in an electric circuit or in a schematic diagram, well, we know that reduces the flow of electrons. The electrons are what flow in an electric circuit. Well, in a water circuit, we have an equivalent of a resistor, like a constriction, a smaller bore of the pipe, and therefore that will resist or restrict the flow of the water in the water circuit. So very similar analogy. And you'll come across one a little bit later on. All right, so pulling back some of the material from the technician class level, we're going to talk about components shortly, or some components. And it's important that we remember what a semiconductor material is. So on the spectrum of whether something conducts electricity or not, we have on the extreme left good conductors that will conduct electricity. And we'll typically consider those to be metals of some type, typically. So gold, silver, copper, iron, aluminum, etc. Those are good conductors. So that's on the one end of the spectrum, where electrons will flow very readily in this type of material called conductors. And at the opposite, the polar opposite end, we have material or substances or components or things that do not conduct electricity well at all. They are poor conductors. And those are called insulators. So for example, glass, rubber, plastics, and so on are insulators, right? They do not conduct electricity, or they do not conduct it very well at all. So those are insulators. So on both ends of the spectrum, we have good conductors and we have on the other end insulators. But we do have a middle ground. We have something in between, and that is called semiconductors, meaning that they don't conduct extremely well, but neither do they insulate very well either. They're sort of in between. They will pass the current, and we take advantage of that property in semiconductors. And semiconductor material, or the substances or the elements, are things like silicon, germanium, selenium, gallium, arsenide, etc. These are all semiconductor material or elements that will allow electricity to flow, not as well as conductors, but not as poorly as insulators. So that's why it's called semiconductors, sort of in between, right? So some of the components that we'll be talking about coming up will be made from, or constructed from, or produced from semiconductor material. All right, so let's remind ourselves what a diode is. We covered this during the technician class, but we'll just repeat it because we're going to talk about some specifications of diodes. So what is a diode? Well, a diode is a component that will allow current to flow in one direction only, not the other. So this is what a diode component may look like on your screen. This is a symbol for a diode, for example, shows which is the positive and the negative. It's polarized. Cathode is the negative, anode is the positive. So this is what a diode is. And we come to the water circuit equivalent. A diode in a water circuit, the equivalent will be a check valve, because a check valve in a water circuit, let's say from your water tank, will allow water to flow in one direction only. Let's say the feed that goes from the supply in Trinidad and Tobago, the water line that comes into your water tank, you want the water to flow in one direction only into your tank. You don't want, if the pressure drops, you don't want that water to flow out of the tank back into the water line. So that's a check valve that allows water to flow in one direction. And that's exactly what a diode does in an electric circuit. Or on a schematic, when you see a diode, it means that the current will flow in one direction, or what we call, as it's forward biased, it will flow in that direction. But if we reverse bias the circuit, it will not flow. And that's the point here. You see here, the check valve, when water is flowing in this direction, the check valve will open and allow the flow. But from the time water starts to try to flow in the opposite direction, bam, the valve is shut and there is no flow. So this is the water circuit equivalent of the diode, and the diode will operate the same way with electricity. It will allow electrons to go in one direction, but not the other. So just some different types of diodes, and we will discuss specifically a type of diode shortly, and we will also you'll see different types of diodes as well. There's not one type of diode. So on your screen, a lot of extra information. You can have a look at these to see the various types of diodes that exist, and also the various symbols that match up the various types of diodes out there. Right, so it helps to remember what practical applications in electronic circuits or in schematic diagrams. Why do we use diodes to construct our circuits? Well, they can be used it's a very versatile component, very simple component, but diodes can do quite a few things. So one of them is rectification, meaning that we can take an alternating current, pass it through a diode, and we will end up with pulsing DC. So that's called rectification. Another thing that a diode could be used for is to do voltage regulation, meaning we want a voltage of a particular value to clamp it. We don't want it above. We can use a diode as well. We can also use diodes to switch radio frequency voltages, right? So on the right-hand side here, we have an example of that. And last but not least, diodes can also grab from the air radio signals and demodulate it. It will take the audio out of the RF. So for example here, there's a little circuit that shows this. See a diode in line there. That diode can also be, so if you're looking at it, you may say, wow, diode could do a lot of different types of things. Yes, it's very versatile. And that's just to give you an example of what diodes may be used for. So again, a bit of extra information to set the context, and hopefully we understand what diodes are. So when we come to specifications, we will know what we are specifying about the purpose of diodes. All right, so let's just show that a diode, we talked about, current flowing in one direction only once it's in the circuit like that. But if it tries to flow in the opposite direction, it will not allow it. So there's a term, and I mentioned it a little bit earlier, called biasing. So we have forward bias, which is where you put the positive to the positive, the negative to the negative, and therefore there will be a current flow. That's a forward biased diode. However, if you apply it in the opposite way, you move it in a different direction, you will in fact apply the negative voltage to the positive of the diode and then the positive to the negative, and this will not flow, right? So current will not flow in a reversed bias condition, right? So if you take your battery here and you flip it and you try to send the current in the other direction, the diode, remember, acts like a check valve. It will not allow this to jump across here. We're trying to bias it like that. We're trying to apply the positive to the cathode and the negative to the anode, and it just will not flow, right? So that's what this positive and negative means here. We're trying to apply that to the diode, and the diode says, I want to be forward biased to allow, I want positive on my anode and I want negative on my cathode. And if I get that, I will flow. But it says, you know what? I see you. You're reverse biasing me. I will not allow it to flow, just like a check valve. So we have the forward bias condition where we have the diode correctly biased. The positive is applied to the anode and the negative is applied to the cathode, and there will be a current flow. Notice in this circuit here, this uh, uh, this will illuminate, right? We have a bulb or an LED or something like that in the circuit. It will light up. Why? Because current is flowing. This other circuit here, where we have reversed biased this diode, we notice that this lamp is off because there's no current flow. So this is just talking about forward biasing or reverse biasing a diode by applying the voltage from your voltage source, as in this case a battery, either in the forward direction or in the reverse direction. In one case it will conduct, and the other case it will not conduct. And there are two different types of material that we use to construct diodes. We'll come to it in a little bit. You have germanium and you also have silicon. And depending on the material that this diode is made from, there's a different voltage threshold that will allow it to conduct when it's forward biased. So for example, in this case here, if it were to be a germanium diode, all you need to have is 0.3 volts voltage drop for this to conduct. Anything less, it will not conduct. So you have a little bit of a threshold. That's called the forward voltage drop. If it is that this diode is made from silicon, and by the way, we say in silicon, note that it's not silicone, right? Silicone is that substance that you could use to seal and use for other things. You make different utensils out of silicone, right? But silicon is the substance or the element that we are talking about, silicon, right? So we're in an amateur radio class, so we should strive to pronounce the words correctly. So silicon, not silicone. So silicon has a 0.7 voltage threshold that needs to overcome for current to flow. And we will come, that's actually an exam question, and we'll come to it in the next slide. All right. Right, so remember a tip that we have: anytime you see something as a bullet point in yellow, 9 out of 10 times, or almost always, it will be an exam question or related to an exam question, right? So the rest of the stuff in white is important information to set the context to help us understand, but the yellow is what you will actually get in the exam. So that's why we try to highlight it so that we know what the focus is, all right? So we did talk about it, that there's a key specification about diodes, and it's called the junction threshold voltage. That is the voltage, that is the minimum you must apply for it to conduct or for it to allow the current to flow. So it's the junction threshold voltage, or sometimes called the forward threshold voltage. So we need to know that term. And as mentioned earlier, there's a difference between silicon-based diodes and germanium-based diodes, right? And that's the material that they're made from. In that, the silicon diode, which happens to be the most widely used, most of the diodes that you'll find will be based on silicon, but you do have germanium diodes. And you need to know that silicon diodes have a higher junction threshold voltage, right? That's the voltage that must be achieved, or you must apply to the diode for it to allow a current to flow through it. Right. So we need to know for the exam that the forward threshold voltage for silicon diode is 0.7 volts. Right? 0.7 volts. It's higher than the voltage, the forward voltage for germanium, which is 0.3 volts. Right. So 0.7 volts and 0.3 volts. We need to learn these for the exam. We just put a little diagram here, a little graph to show that a germanium diode starts to conduct when it's at 0.3 volts. There we go. Notice, however, a silicon diode does not start to conduct until it reaches a 0.7 volts. So we have shown this here graphically as well, so that you know germanium is a little more sensitive, if you want to look at it, and allows flow of current through it at a lower voltage threshold. You need a higher voltage to be able to, higher force, if you can look at it that way, for the current to start to flow in a silicon-based diode. All right, so let's remind ourselves of another semiconductor-based component, and that's the transistor. So we covered this in the technician class, so this should be a refresher for most of us. So what is a transistor? Well, it is an electronic component, and it can be used to either switch or amplify signals. And we have our symbol of a transistor here, and we have what the physical component might look like on a circuit board if it's a discrete or an individual component. Yeah, and we need to know that it can either be used to switch or amplify, meaning to turn on and turn off, or to increase the signal levels. That's what we mean by switch. Turn on, turn off, or move between one and the other, or amplify, which is increase the level, right? So that's what a transistor can be used for. And we, when we amplify, we say that there's gain associated with the transistor, right? And a transistor can provide us, in the case of amateur radios, we always looking to increase power, and therefore we can get a power gain from our transistors in the circuit. It's also important to know about transistors. We need to be aware transistor comprises of 3 regions, and there can be an NPN or there can be a PNP. However, there are always 3 regions of semiconductor material. This one, this one, this one, right? So 3 layers of semiconductors sandwiched like this. And each one of them has a name. So the pin that goes to this conductor or this bit of material is called the emitter. The lead that goes to this one is called the base, and the lead that goes to the last layer is called the collector. So you have the emitter, base, collector, and this is how a transistor is constructed. All right. So we have some other types of transistors here, and it's just for your additional information, for your awareness, references. Further information not required in the main for this course. However, we always like to do something a little extra so you can see different types. You have the NPN, you have the PNP, what we call bipolar junction transistors. We have the field effect transistors, and you have the N channel and the P channel type. You have the MOSFET, which we'll come to in a little while, and so on. And these are different types of cases that transistors may be contained in. So if you see any of these in a circuit, you open up some piece of electronics and you see these types of components, chances are they are transistors. So not everything that looks like this will be a transistor. However, some of them may be voltage regulators, some may be other components, but typically transistors will be in either of these types of packages. Right, so we did say that a transistor could be used as a switch. A transistor can also be used to increase the signal or have gain or amplify. And these two are just circuit diagrams. You don't need to learn it for your exam or anything like that. But we're just showing the practical example of when you're designing circuitry. You have this transistor here, and this functioning as a switch. It's biased in such a way that it will switch on and switch off. And in this case here, it's biased in such a way that an input signal will be amplified or increased, and you have gain. So this is a transistor in a circuit functioning as a switch, and this is a transistor in the circuit functioning as an amplifier. Again, don't need to learn, but just to give you an idea so you can compare and contrast and recognize that what we're saying has practical applications in circuitry. All right, so we now come to our water analogy when we're talking about transistors, right? So we did say a transistor can switch on and off. So this is a symbol for a transistor. Now you may recognize this as a quarter turn shutter valve. You may have this as a garden tap or somewhere, or a different type. But what we're saying here is that this is the collector, and you have the base that is being biased. And then depending on how the base is biased, it will allow flow, all right, in this through the emitter, right, the tap itself. So that's the kind of analogy we're using in the water circuit to describe a transistor that is acting as a switch on and off, for example, right? So just the analogy. Right, so transistors are often used in amateur radio circuits, right? You open a radio, you may see it as discrete components, or they may be actually very tiny surface mount components, or they may even be part of ICs, which we'll come to in a little while, integrated circuits. And this is just regurgitating some of what we just said, but just in a different way. We're stating that transistor can be used as amplifiers and switches. And when it's used as a switch, we're saying that a small current applied to the base, will control a larger current that goes through the transistor from the collector to the emitter, right? So that is what this is saying. Again, this is not really on this exam, but we're setting the context and reminding ourselves what a transistor is about and what we can use it for. And therefore, when it's used as a switch, the current is either flowing or it is not flowing. So we say the current is either on or off. So when it is off, we say that the transistor is operating in the cutoff region, and therefore this circuit will be open so that no current flows between the collector and the emitter, right? So it's like the tap is off. However, when we turn the tap on, then you have flow. And therefore, that is, we say that the transistor is operating in its saturation region. So we have some technical terms. So when it's off or it's not flowing, that's the cutoff region. When it's flowing, when the tap is open and current flows, it's operating in the saturation region, right? And we have some little diagrams to show it's an open circuit, nothing flows, and a closed circuit, it flows. Or cutoff region, it doesn't flow, and in the saturation region, you see there is a current flow, right? So just extra reference information to set the context. We will now come to the exam question, and you'll see why we gave all of that context. So this is an exam question. It says that, well, the point is that the operating points for bipolar junction transistor used as a switch are saturation and cutoff. Now, if we didn't talk about what saturation and cutoff were, this here will seem to stand alone and be contextless, right? So that's why we took the journey and we went through some of the build-up information, the foundational information, hopefully to understand this point or this question that you'll get in the exam. And this is in yellow, so that means it's a direct quote from the exam question. The operating points for bipolar transistor or bipolar junction transistor, when it is used as a switch, meaning to on and off, it's the saturation and cutoff. So remember what the saturation is? Saturation here, it conducts. The cutoff, it does not conduct. So that's the whole point about this question. It's a very summary question, but it takes an understanding of these previous slides here to realize what this point is about, right? So you could always have a look at those slides again and absorb the ideas, and then you will see the relevance or the context of this exam question. All right, yeah, we could do a couple more slides before we take our break. So let's talk about different types of transistors. So we did say, and we showed on one of the previous slides, that there are different types of transistors and they will look differently. So we said that you can have a single discrete component or an individual component called a transistor on a circuit board, and it may look something like this on the board, or we have different form factors. But a transistor could be miniaturized and put into an integrated circuit. And a couple slides from now, we'll see what the inside of an integrated circuit, but you could have literally hundreds, thousands, even millions of transistors that are miniaturized and put into a package like this called an integrated circuit. So you can either have a single transistor, or you could have transistors, many of them, in an integrated circuit. And there are two types of transistors that we have talked about before in the technician class. We have what we call the bipolar junction transistor, or simply bipolar transistor. And we have the other type called the field effect transistor. So we'll just talk briefly about what FETs or FETs are, because we need to talk about MOSFET, all right? So you see, we're trying to build on the knowledge as we go. Hopefully we understand the foundational material, and therefore we build on top of that. So again, we covered all of this during the technician class. We are repeating a bit of it because we know not everyone would have covered all of the material yet. So you see why it's important to go through the technician. We spend quite a bit of time at the technician class level going through this. We are racing it a little further or faster in the general class, right? So that we can make a connection. All right, so we did talk about FETs, FETs, right? Again, not the type of FET that you will encounter on Carnival time in Trinidad and Tobago, any other time. Field effect transistor, that's the type of FET that we are talking about. Field effect transistor, abbreviated FET. What it is, it's an electronic component, and this is what it may look like. Again, you may say, but kind of looks like a transistor, right? Yeah, right. So you need to, how do you know the difference? Excuse me. How can you tell? It's the part number on it will tell you that it's an FET or FET. And it can control the flow of current just like a transistor, but using an electric field, right? So the terms that we use for the three leads for an FET, it's quite different. Remember, in the transistor, we say it's an emitter-based collector. But for an FET, we talk about a gate, a drain, and a source. And the symbol is also different to reflect the differences between an FET, which is a field effect transistor, and a regular bipolar junction transistor, or just simply transistor. Right, so the foxhole runs a little deeper. So we talked about junction transistors or bipolar junction transistors having a collector-based emitter. We talked about a FET, gate source drain, and now we are talking about a MOSFET. which also has gate source drain. But what is this MOSFET about? Well, MOS is an abbreviation for metal oxide semiconductor because there's a substrate or there's an insulating part on the component itself when it's constructed of metal oxide and it acts as an insulator, right? So MOSFET, metal oxide semiconductor FET. So MOSFET. And if we were to look, we have zoomed in here on a MOSFET construction, right? So we have the reverse substrates and we have the type of material here. We have the N type material here. So we notice that we have the gate connected here, we have the source connected here, and we have the drain. So the same gate, source, drain as a regular FET, but we have introduced this extra insulating layer called the metal oxide insulator, right? So metal oxide semiconductor, MOS. So it's just saying that we've introduced this extra layer here in the construction of the MOSFET. So this is the exam question. The following describes MOSFET construction. The gate, which is this lead here, this gate is connected here, is separated from the channel by a thin insulating layer. And that thin insulating layer is made out of metal oxide semiconductor material. Hence the reason this is not a regular FET, this is MOSFET. All right, so yeah, let's do another slide at least before we take our break, right? So before semiconductors became popular, before semiconductor electronics, we had the prior type of technology and vacuum tubes. So on the top right-hand corner here, we have what a vacuum tube might look like. So it might be kind of look something like an incandescent bulb, right? You know, it will light up on the inside and so on, but quite different to a bulb, but it's very similar in the sense you have a glass outer and you have some wires inside there, and it will glow. It will probably even get very hot as well, right? So these are vacuum tubes and the air is sucked out of them, and you have different components in there. You'll have a plate, you'll have a grill, you have a filament. So you pass the current through the filament will get very hot. And when that filament gets hot, it will emit electrons. And of course, those will move inside of there. It's a vacuum, right? The electrons will move and you get different types of functions, different types of vacuum tubes. But the one that we are going to talk about and the construction and the parts that we need to know about is called the triode. And if you're saying triode means three of something, that's you'll be quite correct, triode, right? So we have a little bit of a definition of vacuum tube, and you'll notice that it is very similar to that of a transistor because they predated transistors. We still do use vacuum tubes in today's world. Amateur radio operators, many of times, instead of having a semiconductor based amplifier, we may have a vacuum tube or a tube amplifier. You may hear hams talk about, I have a tube amp, right? So that's what they're talking about. It's not based on the semiconductor type material, but it is using vacuum tubes. So you will see here in terms of the definition, it's an electronic device that is used to control the flow of electrons in a vacuum to amplify or switch signals. Where did we hear that before? Let's go back to it. What did we say about a transistor? We said transistors are used to amplify and switch, right? So if transistors are doing that, let's go back to our vacuum tube slide. Here we say it's amplifying and switching. So it's doing a very similar job. It's except that, it's a different type of construction, the older technology, but it's still relevant today. That's a vacuum tube or tube. So people may have still at home a bit of an artifact, a vacuum tube based older radio. So you may be lucky to have one at home, So we just need to be aware that the construction of the vacuum tube, so this is a diagram of what it is going to look like. So you have the glass outer here, or what you call the vacuum envelope. So vacuum meaning that most of, if not all of the air is sucked out of inside of there. So that's hence the reason vacuum, there's a vacuum in there. And then you have the metallic plates or components, right? So you have the cathode, you have the anode, and you have something called a control grid, right? So we need to be aware for the exam what the control grid does. And when we'll come now to another plate that is put inside of there, called a screen grid, and we need to know what the screen grid, if added into the triode, what it does, right? So let's discuss the two exam questions. So firstly, control grid. So we did say that vacuum tube is consisting of an anode, a cathode, and a control grid. So we have the electrons that are flying across in the free space there. It's a vacuum, right? It's flying across. It's trying to go there to flow. And so you have a current flow that's going on, but you have something called a control grid, which regulates that flow. So let's look at the exam question. Bullet point says the control grid element of a vacuum tube, that's this control grid here, note the dashed or dotted lines, is what does it do? It regulates or controls the flow of electrons between cathode and plate. So you have the cathode here and you have the anode, also sometimes called the plate. So the electrons are trying to flow here. It's going there. But this control grid will control the rate or regulate the flow of the electrons as they fly from the cathode to the anode. All right, so look at that. And there's another addition to some triodes. They will insert an additional, what we call screen grid. So you notice here, if you compare and contrast between these two, the difference between these two is that we have added an additional grid called the screen grid, and we need to be aware of the purpose of that screen grid. So let's go at the exam question. It's the primary purpose of a screen grid in a vacuum tube is to reduce grid to plate capacitance. So let's dissect this a little bit. The primary purpose of what? A screen grid. So here's our screen grid that we added. Notice this diagram here does not have the screen grid. We just have the cathode, we have the anode, sometimes called the plate, and we also have the control grid. And of course, it's all encapsulated in an outer glass envelope to create that vacuum. All the air sucked out. Well, in the same way, this is another type of triad, but we have added a screen grid inside of there. And it is added into that vacuum tube to reduce the grid to plate capacitance. So what is the grid to plate? So you have the grid here and you have the plate. And because of that, there's a capacitance. Remember, if you remember how we constructed a capacitor, you had two plates followed by insulated by dielectric. So you kind of have that sort of capacitor build here, but you don't want capacitance because it's parasitic, it's extra, you don't want it, it's a pest. So what you do is you introduce this screen grid to reduce that parasitic or capacitance, or the grid to plate capacitance. Between this control grid and the plate, you reduce the capacitance because that's not desirable in a circuit. If you want it, that's fine, but it's not the primary reason you're having this triode. You don't want to reduce capacitance. You want to be able to switch, or you want to be able to amplify. And if there's capacitance or parasitic capacitance or extra capacitance or unwanted capacitance, it may affect the function of your circuitry. So folks, let us take a 2-minute break. Maybe get up, take a little stretch, have a bathroom break, probably have a glass of water, and be back in 2 minutes time. Okay, so welcome back. Right, so that's it for vacuum tubes. Now, some of us may say, well, I don't think I've ever seen a vacuum tube. So, if you have ever seen an older television, not these flat screen or flat panel TVs, LCD, OLEDs, and LED TVs, and so on, the older what we call CRT or cathode ray tube type TVs, the ones where they're not flat like a wafer thin. Front to back, they could be a foot or two or um, as much as arm's length from front to back, right? So that glass tube there, in a way, is a vacuum tube as well, right? So just in case you're thinking you have never seen a vacuum tube, if you see, have seen one of the older TVs, not the flat panel LCD, OLEDs, or so on, the earlier type of televisions which still exist around sometimes, those are vacuum tubes. All right. So let's discuss batteries, or someone will say batteries, right? So we may be familiar with batteries. We may, for example, on the right-hand side here, you see different types of batteries. You have the 9-volt battery, you have the 1.5 volts AA battery, 1.5 volts AAA batteries, and different types of batteries of different voltages as well. And batteries may have different types of chemistries. So you may have lead acid battery, you may have lithium ion batteries, you may have nickel metal hydride, you may have nickel cadmium or NiCads. And several other chemistry types depending type of cells that are used to create the battery, right? So some of them are one-use or single-use batteries. Some of them are rechargeable, and we need to be mindful of the type of batteries so we don't misuse and abuse them, and we are safe, right? So in amateur radio, you will find that we do have batteries, typically rechargeables, but we may use other types of batteries as well. And we may use them in our walkie-talkies or handheld devices, or portable or radios, handheld radios really. And batteries are very good for emergency communications purposes. So if we are operating at home and we were to lose current, lose power from the supply, from the provider, we still need to operate, especially if it's an emergency conditions, and batteries are what will keep us up and running. So you may charge it up how you wish. Still, you can have solar, wind power charging it up as well, renewables. But the idea is that you have battery storage. So these are some of the chemistry types that we have. As you said, nickel cadmium used to be quite popular. Now we have nickel metal hydride and even lithium ion phosphate batteries that are quite popular today, much lighter. Right? But we do need to know something about batteries for the exam. So we have a couple of bullet points. The first one is that a battery can have an internal resistance, right? And if the battery's resistance is low, that means we can have a high discharge current, and that's an exam question. So here it goes. An advantage of batteries with low internal resistance is that they can supply a high discharge current. And we're just making a reference here to Ohm's law, right? So where the current is equal to the voltage divided by the resistance. So we recognize here, due to this format of the formula, if the resistance is low, that means the current will be higher. Right? If the resistance is high, current is lower, right? That's just the inverse relationship. So to understand what this means here, if the resistance is low, or the lower the resistance, the higher the current, right? So this is just a Ohm's law reference. Hopefully it will help in understanding this point, that you can get a high discharge current, or current could be high, if you have a low resistance or a low R, right, for a given voltage. Right, so another type of battery, you may recognize this, you say, wait, this looks like the battery you'll see inside of a car or vehicle, right? So yes, so if you have a boat, you see something like this. So we have the types of batteries, car batteries, what we call cranking or starting batteries. And then we'll have the other type of batteries that we call deep cycle batteries, often used in the marine environment or even for UPSs, right? Because they can just be discharged a little bit lower. As a matter of fact, the difference between the two often is the thickness of the plates that they constructed. Right? So we need to be aware of these, what we call 12-volt lead acid batteries, right? So we call them 12-volt batteries. If you were to measure the nominal voltage, it may be much higher than 12 volts. but nominally 12 volts, right? 6 cells at 2 volts each, approximately 12 volts, right? So this is what it will look like. And we have this symbol here again for the battery to remind ourselves. But we need to also be safe. We also need to not waste money as well. We need to make sure that we treat batteries with the respect that they deserve from a safety perspective, as well as we need to make sure that we treat them the right way in terms of charging them. We don't want to discharge a battery such that the voltage drops below a certain level. You want to discharge them too low because that can have lasting damaging effects on the battery. So we need to be aware of what is that minimum voltage. Shouldn't keep it at that for too long. We don't want to discharge them all the way. We must always charge them when they need to be charged so they will perform optimally. But we do have an exam question in relation to lead acid type batteries. And that is the minimum allowable discharge voltage to attain the maximum life of a standard 12 volt lead acid battery is 10.5 volts. What this is saying is this type of battery here, you do not want the voltage when you measure it to go down to less than 10.5 volts. So nominally it's a 12 volt, maybe a little higher. When you measure the voltage, don't let it go below 10 volts because that could have lasting damaging effects on the battery, and it will shorten the lifespan. So if you want to maximize your investment, you want to maximize how long after you purchase a battery it will last for you for a couple of years to come, you just want to make sure you don't let that voltage drop less than 10.5 volts, and it's an exam question. The minimum allowable discharge voltage for maximum life of a standard 12 volt lead acid battery is 10.5 volts. All right. Okay. So Ramzan, yeah, Sylvania TV in the 1970s. Yeah, that's what we're talking about, right? Right. So now, so Fahad, no battery should be discharged completely, right? Each of them will have a minimum voltage threshold beyond which you can damage them, right? So each one will have a difference. So some of them are deep cycle and they can go low for a little bit longer and a slightly lower voltage, but no, you don't ever want to completely discharge, So yeah, good question. Excellent, guys. All right. So we now come to talk about ICs, integrated circuits. Cover this in the technician class. So we're just repeating some of the information here. What is an integrated circuit? Well, it can look like something like this. This is the package here. You have the pins and you may have hundreds or thousands of transistors on other components side of there. And this is what the symbol might look like in a schematic diagram for an IC. Of course, you have microprocessor type integrated circuits that have many more pins than this, right? So these are simpler ones. So an integrated circuit is a device that combines several semiconductors and other components into one package. So you can have capacitors and resistors as well as transistors and MOSFETs and other things inside of there. Integrated circuit, that's what it means. More than one component, or many, sometimes millions of them inside of one package. Integrated circuit. So it's a miniaturized circuit consisting of multiple components, transistors, resistors, capacitors, diodes, and they are interconnected within the same package, right? So again, extra information here for you. And it's good to know because it's an exam question coming up that they can do analog or digital functions, right? So a bit of extra information and a refresher from the technician class. So we did promise you what the inside of an IC look like. So if you were to cut it open, slice it open, and use a powerful microscope and zoom on in, this is what you'll see. Look at all these are components. They're discrete components that have been miniaturized and they're all connected up to each other inside of there. So miniaturization has millions of components in there. Hence the reason we call them integrated circuits. All right, so in our amateur radio equipment, we do and tend to have lots of integrated circuits. We may have microprocessors and so on inside of there, and they may have millions of transistors. And of course, in an IC, it could be an analog only IC. It could be a digital only IC, meaning analog circuits or digital circuits only, or it can have a hybrid. You can have some analog circuit in there and you can have some digital circuits in there, combination, right? But one of the types of integrated circuits that we need to know for the exam is called an op-amp. Now, an op-amp is short for operational amplifier. So the exam question, and in an integrated circuit or IC, operational amplifier, op-amp is an example of an analog device. So we just need to know that an op-amp is an analog device. And we have here what the symbol will look like, and also what it may physically look like as well, right? An op amp, operational amplifier. Exam question. Right, so up next, another type of integrated circuit called an MMIC, monolithic microwave integrated circuit. And we have a picture of what one might look like here, right? So often used in transceivers or transmitters. And it is an IC, but is a bit more sophisticated as an analog IC than some of the others. One of the reasons is that it operates at radio frequency. So we just have a couple of graphs here to show where the microwave region is on the spectrum, right? But you just need to learn that MMIC stands for monolithic microwave integrated circuit. So we just put this as an aid to memoir where we have the microwave range of frequencies here, so that we know the M is microwave, monolithic microwave integrated circuit. And there it is. Exam question. All right. So we now come to talking about some different types of integrated circuits. One is called the CMOS, and not the drink, right? And the other one is called the TTL, right? So two types of integrated circuits that we need to be aware of. And on your screen, we have what we call the CMOS logic. And on the right-hand side, we have the TTL logic. So again, you don't need to learn this for the exam, but this is just to compare and contrast. And you can see here, you have both types. You have the CMOS chips and you have the TTL. You may say, but I can't really tell the difference. Yeah, well, sometimes you cannot, oftentimes you cannot, and you have to look at the part number to tell whether this is a CMOS or this is TTL or whatever it is, right? The part number is important. These packages are standard packages and may be used for different purposes. So what is this CMOS about, and what is this TTL that we are talking about? So CMOS is an abbreviation, acronym really, for complementary metal oxide semiconductor, CMOS, right? So just for your information, extra information, it uses FETs, or field effect transistors, inside of there, right? Also CMOS, by the way, are very sensitive to static electricity. So when you're handling CMOS, any type of CMOS at all, you have to be very careful that you don't zap it, so you have to ground yourself off, maybe use static, anti-static mat, and so on, right? So CMOS, and that's one of the differences, right? Just for your information, need to be handled very, very carefully. You don't want to zap it, especially in some countries where the humidity is such that, sometimes you're walking and you go and you touch a vehicle and bam, you get a zap, or a door, you get a little zap, or you walk with a certain type of material clothing and all of a sudden now your hair is standing up on end, or you just touch something and you get a zap, right? So static electricity. CMOS type components are very sensitive to that. This is just for your safety and to save you. You don't want to zap your CMOS based chip just because you weren't aware of the sensitivity to static electricity. So CMOS type components use FETs, but you need to know CMOS, complementary metal oxide semiconductor, versus TTL. But what does TTL mean? No, TT is not Trinidad and Tobago here. It's TTL, it's transistor logic, TTL. And those types of circuitries use the regular bipolar junction type transistors, right? So that's the difference between the CMOS and the TTL. And for the exam, this is what we need to know. That an advantage of CMOS integrated circuits compared to TTL integrated circuits is that low power consumption, right? So that's an advantage of CMOS compared to TTL, low power consumption. But remember, it is also very sensitive to static electricity. So you have pros and cons to everything, just like in life, right? So this is an exam question. CMOS compared to TTL, low power consumption, right? There you go. All right, just a little bit of extra information as we're talking about chips, ICs, and so on. And, a type of integrated circuit is called ROM, or read-only memory, or memory that you'll have in your computer. So this is not on the exam, but this is just some extra information that this is also a type of IC, ROM, read-only memory, that you'll find in your computers, right? So ROM chips. You have RAM and other types, but this is ROM, read-only memory, right? Never changes, and when you power off the computer, the ROM information in there is still retained. Okay, so just a bit of extra information while we're talking about chips and ICs. All right, so back to some things that we need to know for the exam. So on the bottom of your screen, we have a transceiver or your radio, right? It's a wonderful HF transceiver, modern looking. And there are a couple of things that we need to be aware of when we define our components of a radio. You'll see a screen. Many modern transceivers will have a screen like this, and as you turn the knobs, you'll see values changing here. As you receive signals, you will see like a spectrum analysis. You will see your voice audio levels and modulation and spectral view, right? And frequency display and the type of filter that you're using and whether the radio is transmitting or not, and maybe even the time, and so on, as well as the meaning of these buttons that are soft keys on the side. What does it do? And this display here is typical of modern transceivers, better ones for sure, right? So these displays often comprise using liquid crystal displays or LCDs, but there are also other types of indicators like lights. So for example, this is the power button here, and this is shining, or it is glowing, or it is lit up in a green color. And this is not an LCD, this isn't a liquid crystal display, but what this is an LED, light emitting diode. Yes, it's a type of diode, but when forward biased, will give out light. Right, so you'll notice here that an LED looks like, the component looks just like a diode, except that you have these two arrows showing that it gives off light. So we need to know that for the exam, that there are LCDs and LEDs on our radio equipment. And one of the other things about LEDs is that the LED will emit light when it's forward biased. When it's reverse biased, it will not typically give off light. However, the LCD in and of itself does not really give out light. You need a backlight or something like that. But what the LCD does, it sort of becomes opaque as the voltage is applied to the screen on the LCD. And that's how it functions. And you often need a backlight to show up. If the light is off, you may not see much on the LCD. Whereas the LED, once voltage is applied, it gives off that light so you can see it. The LCD will need an extra lighting or backlighting. So for the exam, we need to know that an LED, which stands for light emitting diode, and it kind of says what it does, light emitting diode, LED, it actually emits light when it is forward biased. Remember, we talk about forward biasing. You apply a positive voltage to the positive conductor or connection, and you apply a negative voltage to the negative connection. When you do that, you become forward biased and a current flows. If you reverse bias something, you apply the positive voltage to the negative lead, and vice versa, the negative voltage to the positive lead, then you will not have current flow. It will be reverse bias. So the point here is that they're saying that LEDs actually emit light when they are forward biased, and therefore current flows through them. Exam question. All right, so I think the last, so it's we're just about on the hour. So this is the last theoretical concept that we'll be talking about, and then we'll go straight into our question pool, right? So last couple of slides. All right, so as an amateur radio operator, while you are constructing your amateur radio shack, as we may call it sometimes, that's where you will house your equipment, or you're connecting up some transceiver equipment into your vehicle, you'll find that you need to connectorize, and you need to connect, you need to jumper, you need to bridge two devices together. You may have a radio that you may need to power, you may need to send an audio signal in or out of the radio, and certainly you need to connect your antenna to that transceiver or the radio. And you have different types of connectors that we need to be aware of. So for audio frequencies, so you may be familiar with these, sometimes the older VCRs connecting to a TV may have used these. If you had component type sound systems, you may find these, and then they're using different other ways as well for audio and video. And these are called RCA phono jacks, right? So it is an exam question. You'll see the exam questions coming up in the next slide, right? So this is just to introduce it. These are RCA phono jacks, and they're typically used for audio signals, or AF. And the AF here means audio frequencies, right? So phono jacks. But we also have a couple of other connectors like these on the right-hand side here that are used to connect antennas or to connect radio frequency components. So an radio connected to an amplifier or connected to a tuner, connected to an antenna. We will use cables, typically coaxial cable, and these are some of the connectors. And each of these connectors will have a property or a specification, a pro and a con for use in different circumstances, such as depending on the frequency that you're using. Right? So that's the information we need to know about. So we have the RF type connectors, which are these on the right hand side. These four here, they are given a name. So whereas these connectors for audio frequency use is called the RCA phono jacks, we have these connectors that are connecting onto cabling, antenna cabling connected to the back of the radio or to the antenna itself, or any other radio frequency component. Maybe it's a antenna tuner, maybe it's a power meter or an SWR meter. These are the connectors. So you have the PL259 is one. You have the N-type connector, as it's called. You have the SMA type, and sometimes you have the reverse polarity, SMA, but you have the SMA type. And then you have the twist-on type here called the BNC. And each of them can be used and are good for up to a particular frequency. So we'll come to the exams question a little bit, but the PL259 is good for up to 150 plus megahertz. The N-type is good for up to 10 gigahertz. It's also moisture resistant. The SMA connector, that's this one here. It's a small threaded connector and it's good for up to several gigahertz. And then we have the BNC connector. It's a twist lock type. You push it in and twist and it locks, and it's good for up to about 4 gigahertz. So these are some of the properties, and let's get to the exam questions based on these connectors. Here we go. So again, what's in yellow is taken directly from the exam question, the question pool. So the connector type commonly used for low frequency or DC signal connections, read that as audio signals, to a transceiver is the RCA phono, and this is what it looks like. So several of us may have seen this before, right? Audio frequencies. Sometimes it's used for video as well, right? So the RCA phono jack. Next up will be an SMA connector. That's the SMA connector here, right? At least the male. Is a small threaded connector. So you notice the threads here. So you have to screw it and turn it to tighten it. And it's suitable for signals up to several gigahertz, right? So that's an exam question. That's what the SMA connector looks like. And this is the specification that it can be used in, the application, the use case. Then we come now to the BNC connector, and it says that a typical upper frequency limit for low SWR, remember SWR is standing wave ratio, operation of a 50 ohm BNC connector is 4 gigahertz. So you need to learn those properties for the different types of connectors. Right? So above that, above what we spec for the connector, it's going to be a poor connector for those purposes. But as long as it's less than or equal to the maximum of spec for the connector, it will work quite well. So hams will choose the appropriate connector for the frequency band that they're using. And last but not least, the N-type connector. That's this here. It's a threaded connector, very secure, very strong type connector, a little more expensive than some of them. And it's good for up to 10 gigahertz, and it's also moisture resistant. You can tell by just looking at it, right? It's constructed alone. So folks, that's it for the theory. We will just now quickly have a look at the actual question pool associated with all of the theory. So let's go. First question in the question pool: what is the approximate forward threshold voltage of a silicon junction diode? Well, we did say for silicon, it's 0.7 volts. The next question, very similarly, except they're asking us the same thing, but for germanium. So what is the approximate forward threshold voltage of a germanium diode? It's 0.3 volts. All right. So 0.7 for silicon, 0.3 volts for germanium. If you need a aide de memoire, well, just kind of think that the 3 looks like the lowercase g as it's typewritten here, right? So maybe that's a good aide de memoire. Other than that, just to note that what the forward threshold voltage means, it means the voltage that you must apply before the diode starts to conduct, before it allows current to flow. That's the interpretation of forward threshold voltage. Okay, let's continue. Which of the following describes MOSFET construction? So we showed what it looked like on your slide, and we said the gate is separated from the channel by a thin insulating layer, right, of metal oxide semiconductor, right? Okay, next question in the question pool. What are the operating points of for a bipolar transistor used as a switch? Remember we said that the regular transistor can be used either as a switch or to amplify. But when we talked about it being a switch, we did say that the two properties when it conducts versus when it doesn't conduct, we said it's saturation and cutoff. So those are the two terms. Okay, let's continue. All right, next question in the question pool. Which element of a vacuum tube regulates the flow of electrons between cathode and plate? So let's dissect this question. So we're talking about a vacuum tube, but we want to know which of the elements. Remember, we have the cathode and the plate, or the cathode and the anode, as well as the control grid. They want to know which of them is used to regulate the flow of electrons between the cathode and the plate. So the one we learned about, it's called the control grid. So notice they have screen grid in there to try to tie you up, but you know that the screen grid is not used for that. If employed in an actual tube or in a vacuum tube, it is not used for that purpose. It's actually used for something else, which is the subject of the next question. What is the primary purpose of a screen grid in a vacuum tube? And we said it is to reduce the grid to plate capacitance. So you have the grid and you have the plate or the anode, and because there are two plates, remember that's what a capacitor is constructed like. You have two plates at some distance, and you have a dielectric material in between. So therefore, that's what the tube is setting up, and you don't want that. You don't want that extra capacitance, what we call parasitic capacitance or stray capacitance or extra capacitance, unwanted capacitance. So that screen grid that we introduced into the vacuum tube is to reduce that grid to plate unwanted capacitance. All right, let's continue. What is an advantage of batteries with low internal resistance, right? So remember, V is equal to IR, so therefore I is equal to V over R. So if the resistance is low, the current is high. So you get a high discharge current. So you see how the formulas can help us understand material. Okay, what is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery? Let's dissect this question. What are they asking us? They're asking us what is the minimum allowable discharge voltage. So the answer has to be something volts. But for what? It is for maximum life. But for what? For a 12-volt lead acid battery. So we learned that you don't want that 12-volt battery to be discharged to a value of less than 10.5 volts. It could damage the battery and shorten its life. Next question in the question pool. What kind of device is an integrated operational amplifier, or op-amp? Sorry, we said, is it digital? No, it's analog. So an op-amp is an analog IC, or analog integrated circuit. Okay, next question in the question pool. What is meant by the term MMIC? Well, they give you all sorts of things here: metal, monolayer, mode, modulated, multi-mode. We didn't learn that. We learned about it's a monolithic microwave integrated circuit. Remember, this MMIC is operating in the microwave radio frequency region. So it has to have microwave. So monolithic microwave integrated circuit is MMIC. Not this other stuff that they're trying to distract you with. All right. Next question in the question pool. Which of the following is an advantage of CMOS integrated circuits compared to TTL integrated circuits? Well, we did say that, a couple differences. We said that the CMOS is a little more significantly more sensitive to static electricity, and you can fry it. But that's not what the question is about here. This question is about the power consumption. So we're saying that the CMOS has a lower power consumption compared to the equivalent TTL, transistor logic. The CMOS is lower power consumption, and that's the answer. Next question. How is an LED biased when emitting light? So let's break this question down a little bit. How is an LED biased? What is an LED? It's a light emitting diode. So if you want it to conduct current so that it will glow, it will light up, you have to forward bias it, which is the answer. If you reverse bias it, no current will flow and it will not light up. All right. Okay. Next question up is, which of these connector types is commonly used for low frequency or DC signal connections to a transceiver? So it's not the PL259, it's not the BNC, it's not the Type N connector, but it's the RCA phono jack or RCA phono connector. It's used for low frequency or DC signals. Right. Next question. What is an SMA connector? Well, the definition, it's a small threaded connector. It's small, it's threaded, and it's suitable for signals up to several gigahertz. That's the answer. All right, next up. What is a typical upper frequency limit for a low SWR operation of 50 ohm BNC connectors? So let's dissect this question a little bit. What are they asking us? What is the typical upper frequency limit? So it's something megahertz, kilohertz, gigahertz, terahertz, it's going to be some frequency. But what is the upper limit they want for a low SWR for a 50 ohm connector? But what? A BNC connector. And we had learned that a BNC is good for up to 4 gigahertz. All right, last question in the question pool. Which of the following describes a Type N connector? So it's well constructed, it's moisture resistant, it's an RF connector, and it's good or it's useful up to 10 gigahertz, right? So one of the better or the best connectors that we have been talking about, and often used in commercial UHF and above, very good connector, a little bit more expensive, but really, really lovely connector. All right. So let's go back to our slide deck. Right. So those who have been following, we have dealt with pages 21 to 27 in the No Nonsense Guide. All right. So folks, just a reminder, if you have any questions, feel free to send an email to this email address. You can also send a WhatsApp to this mobile number. So we have started sending out a little bit of updates via WhatsApp as well. Some people it's more convenient. This is the WhatsApp channel. You're welcome to join it. We also have additional information that we'll share from time to time on that channel. So you're welcome to join. And we will be placing, for example, every week, the link to the Zoom session as a reminder as well. So if you use WhatsApp, you're welcome to join this channel. You'll get this in your slide deck when it's circulated as well. Right, so we have several of these students, I think about half, that have already joined the channel. So great stuff. So feel free, anyone else who would like to, it's optional for you. All right, so our next session, God's willing, will be next Friday, which is the 1st of December, I believe it is, 2023. Usual start time, 8:30 p.m. So folks, thank you very much for staying the course. Great to have you. Keep on studying, keep on, reviewing, keep on taking those practice exams. For persons who have not yet completed the reviewing the technician class material, we encourage you so to do. So folks, do have a good night. Do have a great weekend. Be safe out there. Take good care and see you next week. Right, so Arthur, the lifespan of a vacuum tube is quite variable. It depends on the usage, and I mean, like anything else, you can have a lemon as well. I know guys have been using vacuum tubes for a few years. Then after they start to get weak, they get, they deteriorate and so on. I think it's quite a wide range, but you can get a couple of years. Difficult for me to say what that range is. And yes, they are available. There are places that do still sell tubes in Trinidad. I think you can still get from Steve's, I believe. Gopal's may still have as well. But many, of course, persons buy online. It's not as popular as it once was. So I think people typically maybe have old stock. There may be some aficionados that may still have, you can reach out to the community if you're looking for a particular tube type. But for the vacuum tubes that I use, amateur radio equipment, such as amplifiers, guys typically purchase them online, right? to replace. And of course, they have to be very, very carefully handled, packaged very well, otherwise they can be damaged. So excellent question there, Arthur. Thank you so much. All right, so everyone, do have a good night. Take good care.